Okay, well, thank you for the opportunity to present today. So today I'm going to talk about the type 2 superlattice materials that we've been working on. And so this is for mostly thermal imaging applications. So my company is IntelliEPIR. So the company is in Richardson, Texas. So basically, if you don't know, that's a suburb of Dallas. That's where we're like 2 exits away from TI headquarters, pretty much. So it was founded in 2010 as an advanced R&D operation for infrared materials development, with in conjunction with intelligent epitaxy technology. So that's actually sort of our affiliate company that really does the back-end manufacturing. So we're more of an R&D outfit. So we leverage that infrastructure. So we have about 4 full-time employees, but at the same time, intelligent epitaxy technology has over 40 employees. So we're really able to contract that resources on an as-needed basis. So it's a small company with a little bit more muscle than just 4 people. So the revenue breakdown is about 85% government contracts, about 15% commercial. And we have collaborators from NASA, from the various groups. And then we have Department of Energy from some SBIR contracts. And then we have defense companies such as L3, Raytheon. And then we also work with Q-Magic, which is also, I guess they were supposed to be here, but he couldn't make it. So they also have some SBIR contracts, and we work closely with them as well. And we also work with University of New Mexico and Texas State San Marcos. And we're a C Corp, and we're not a minority or woman-owned business. Okay. So for the NASA funding, so far we've received our first phase 1, 2, and then actually a phase 2E as well. So that just about, the phase 2 is about to be completed. And then we received another phase 1 for another one as well. So the phase 1 and phase 2 was primarily to develop materials, and we focus on the mid-wave applications. And then the second phase 1, we're moving to longer wavelengths. So this is 8 to 12 micron spectral band. So we actually been working closely with David Ting at JPL. So there's an infrared group there under Dr. Suras Granapala. So we've been working with them. And so the TRL level is sort of between 3 to 4, depending on which spectral band. And then we also have additional SBIR, CTR funding from DOE and DOD as well. Okay, so what progress have we made so far? So under the phase 2 SBIR, the first batch, so we actually try to grow the epi materials. So that's kind of our primary focus, is to develop the strain layer superlattice epi materials, and we did it for the midwave, and this is in conjunction with NASA JPL. And so we actually grew materials on 4-inch epi wafers, and we delivered them to JPL for prototype processing. And this is actually what they did. They made a focal plane array. So this is a 1K by 1K with 20 micron pitch. So there are 9 of them here. And then from one of those, they stuck it in a camera to evaluate. And this is a thermal image taken with one of our people when we visited JPL. So this is a 1K by 1K image. And then on top of that, we've also, on the recent phase 1 SBIR, we also try to push out the cutoff wavelength. We got out to 11 micron. And okay. Wait a minute. Did my slide get so what is unique about our technology? So basically we do infrared materials development. So with the SLS material, you're able to get fairly high quantum efficiency and high pixel yield and then relatively low dark current. So compared to, in theory, it's supposed to have better quantum efficiency than mercury telluride, but although that's not been demonstrated at this point. And also with this, unlike other technologies such as QUIP, there's no need for grading to do the coupling, so it's actually fairly easy to process. And with the gallium antimonide substrate, up to 4 inches now available, so very large format focal plane array is definitely possible. And then by leveraging the 3.5 compound semiconductor manufacturing, so just for perspective, like the compound semiconductor based on gallium arsenide, indium phosphide material system is on the order of like 1 million wafer usage on a yearly basis. So by leveraging that infrastructure, it makes this technology more viable. So one thing that we do is we do epi manufacturing on a multi-wafer production MBE. And then, so by doing this, there's an opportunity for rapid technology development and transition, because when you do it on a production system directly, you don't have to redevelop the technology. And then also, because this is done on something that's on a commercial type platform, so there's a stability for making sure that the technology doesn't just go away. It's not like a one-day deal and then it disappears. Okay. So this is our, let's see, the picture of our production MBE reactor. So, so basically this is the, what a reactor looks like, an MBE reactor. So this is basically an ultra-high vacuum chamber. So you've got a bunch of source ports on the bottom, and then you've got mechanical shutters to open and close. And the base pressure for this thing is on the order of 10 to the minus 10 torr. So it's like being in space, but on the planet Earth, I guess. So with our MBE system, we've got the one we're using for antimonide work, we've got a 4x4 inch configuration and with 10 ports. And then, so we can handle anything from 11 by 2 inch, 6 by 3, 4 by 4, or we could handle a single wafer up to a single 8 inch. And then we have proprietary in situ sensor monitoring for real-time process control, so we can control this process. And then and we also have a production MBE, a larger platform such as a Revere 6000 that we can scale up to. So this one can do a 4 by 6 inch. So for example, if we try to do a metamorphic technology on gallium arsenide, we would have a platform that can address this. And this system can also handle up to 12 inch. And we have a full characterization lab that could to support this material. So we have a class 100 clean room. So it's got kind of clean wings with where we don't do any destructive testing, and then kind of the dirty side where we break the wafer and do processing. So we have a full suite of characterization equipment, from X-ray, photoluminescence, defect map, white light reflection spectrometer, Hall measurement, and contactless resistivity mapping, different various types of CV measurements, and a parameter analyzer. And then we also have wire bonder and a wafer flatness measurement, as well as various device testing for the for the infrared detector material from 77K and up. And so we do some limited device processing, but not on a production scale. And then in addition to that, we also have access to the gallium antimonide substrate manufacturing. So this is a crystal puller, so actually it's pulling crystal. And then, so this is a puller, can handle up to, it's got a 10-inch diameter quartz boat, so it can actually, so we could pull pretty, large diameter ingots. So here's an example of our large diameter ingot. So from here we can cut out 2, 3, and 4-inch readily available. And then we also have polishing tools. So this is a picture of the flatness of one of the wafers that we measured. So before EPI, we could get to about 5 micron flatness from up to 4-inch. So when you're trying to make focal plane arrays, that's very important, because if the wafer is warped, when you try to do lithography, then it's the registration won't align right. And when you try to do hybridization, then you have bad pixel alignment with the readout, and then I guess our customer would complain, so that's kind of a bad thing. So we try to keep the wafer as flat as we can. And just in terms of our experience, we've actually, this is some of our previous work where we actually did some work that was flown on a satellite. So we actually grew the QUIP. These are the 3 QUIP EPI focal plane. We grew the QUIP EPI that was made into a focal plane arrays, and this was actually the TIRS instrument on the Landsat 8. So this is a Goddard, a NASA Goddard project, and we're fortunate enough to participate as the EPI provider for this. And this was the very first thermal image. So, so this one actually has 2 bands at 10.3 to 11.3, and then 11.5 to 12.5. So when I saw this image, I was relieved, because I know that in our business, if something goes wrong, the EPI guy gets the blame. That's sort of guaranteed. And so we think this type of capability and understanding that we have developed should definitely apply to our efforts as we move forward into like the type 2 superlattice as well. So we do have that understanding, and we know what it takes to kind of get the products out there. Okay. Now I'm going to talk a little bit about the various technologies and how they compare. So, there are all these different technology, from silicon microbolometer, MCT, mercury cadmium telluride, InSpi, and then gallium arsenide-based QUIPs, and then gallium antimonide-based strain layer superlattice. So in terms of operating temperature, silicon microbolometer is really very good for the uncooled. So everything else is all cooled, unfortunately. But for the higher performance market space, pretty much everything is going to be cooled. And then for the mid-wave band, so the uncooled is not going to be able to compete with the cool detector. So really the best detectivity is mercury cadmium telluride. And then InSpi is also very good as well. And then gallium arsenide is okay. And then the type 2 superlattice is very good. And but the one advantage of the type 2 superlattice is, well, with InSpi you have to go to about 80K to operate. You can't go much higher. But with like Lockheed's demonstrated some type 2 material system with the NBN, and then I think HRL has demonstrated that as well, where they can operate up to 150K for mid-wave type applications. So for the long wave, pretty much I would say MCT is very good detectivity, and then InSpi doesn't apply just because that's the band gap is too large. And then QUIP is kind of okay, but the type 2 superlattice is very promising as well. And in terms of manufacturability, obviously silicon is excellent in volume, but if you don't get enough volume, that's also not easy. And then for MCT, the challenge is while the detectivity is very good, it's generally harder to get high yielding focal plane array with no blinkers and all that stuff that the focal plane arrays people kind of were concerned about. With INSPE, it's very good, but it's limited for only mid-wave. And then with QUIPs, you can get very good performance in terms of manufacturability. And then with type 2, it's actually up and coming, and we feel that eventually it can catch up very quickly. And in terms of the cost, it pretty much kind of, silicon's the lowest, and then MCT is obviously the most expensive. And everything else is sort of, I would say, in the medium range. So, and then in terms of, oops, sorry, let me go back one. And then for large diameter size, gallium antimonide actually is actually pretty good because 4-inch is readily available, and but MCT, even though it's got the great performance, the substrate's extremely expensive. To get kind of the same substrate, you'd spend like over $10,000 for 4-inch equivalent easily, just for the substrate with no detector material on top. And then let's see. And I think I've covered everything. Yeah, so anyways, for type 2, we believe that it could definitely handle the larger substrate size. It could support that for, say, if someone wants a very large focal plane array on a 4-inch, that can be done. So you could do like a 4K by 4K or something crazy. So in terms of NASA application, so this is a high, performance infrared material. So it's, good for a lot of NASA, Earth planetary science and astrophysics missions. So you guys probably know this better than I do. And then, so for example, the Europa Jupiter system mission. So that's some of the possibilities where this could be useful for the mid-wave application. And then hyperspectral infrared imager. So if we can push out the cutoff wavelength and get quantum efficiency to be very high, then you definitely get the performance out of those. So that, because this is a broadband detector, so it's and highly uniform. So there's a lot of potential that can be done with this. So I would say the technology has shown pretty good promise, but there's still a lot of work to be done to improve on this. And then obviously, we've already got a TIRS instrument with QUIP, but I definitely see that if there's another one up and coming, the type 2 superlattice would definitely, I think, will kind of beat out the QUIP hands down. So that would be sort of a no-brainer. For non-NASA application, obviously, there's the thermal imaging for military applications, so such as on the aircraft. So, for example, you could have a hot mid-wave replacement for INSPE or for space applications and surveillance as well. And then obviously there's some other application for trace chemical analysis for hyperspectral imaging, and then biomedical applications such as tumor identification, and those are some of the possibilities. So what is the challenge in this sort of market space? Well, actually there's a lot of people that build focal plane arrays and cameras. However, the key for this stuff is to actually get the photosensitive detector material. That's much, much harder to come by. So especially for the type 2, is not readily available at this point. And it's in development. So that's really the high barrier to entry is people can't get the materials. And then also, even if you do it in a research system, the question becomes, can you actually make it scalable? And if you develop it on a single wafer system and then you try to transfer it to a multi-wafer system, it's like redoing the recipe all over again. It's Groundhog Day sort of a situation. So we just sort of take the approach of developing the technology directly on a multi-wafer platform. So really kind of have a mindset of a production built into the way we do the business. And we think that's important. So in this material system, because it's so new, it's not just growing epi, but actually there's a lot of understanding of the devices. So part of our focus is to develop infrastructure and understanding so we can actually work with the customer and help them to sort of design and custom tailor the epi products to meet their applications and their needs. Because everyone's got a different flavor of what they want for the way they process things. So we have to really address that effectively. And that's, I think, is our value proposition. And also, if you only need a few wafers to develop now, and then you buy a whole reactor just to do this, it would be very expensive. But by having sort of an epi foundry that various groups can leverage resources, it reduces the cost of doing business. Because otherwise, if you have 1 MBE for each facility, you have 10 companies, and I think NASA would run out of budget pretty quick. Well, maybe not, but and also we do the multi-wafer development. So this means once the technology is developed from R&D, you could basically go to production very quickly because the recipe is already developed. There's no transition or anything. And then we also have the ability to scale up to larger capacity on as needed basis. So that means possibly larger size substrates. Okay. So in terms of business development strategy, so the way we do our business is we actually try to engage our customers and the FPA fabrication houses early in the process. So we see them more as a partner and collaborators, and so we help to grow the market together with them. So, and this is important because if you don't start from the beginning and then you kind of come in later, things may look good, but it may or may not be compatible with their process. So we have to really pay attention to that. And then also, we're really an epi foundry, so we're really not interested in the marketing, and we really don't know it that well in this market space. So we find that it's more effective to leverage our customer marketing capability, because the Raytheon and L3 or the Lockheed of the world, they know who the customers are. We really just prefer to focus on what we're good at, which is to produce the materials. And then we obviously pursue some external funding with our customers or do something jointly all the time. So, as an example, we leverage some SBIRs for joint technology development. So this is actually work we did with QMagic. We supplied the EPI for them, and then they develop a focal plane array. This is a second generation 640 by 512 camera. So they took a picture of an aircraft taking off. They're in Nashua, New Hampshire, so I asked if they went to Logan Airport, and they said no, he went to Manchester. I think if you go to Logan, you might not live to tell about it. So, so this is really, I think, a viable technology. If you look at this image here, you can actually see the heat signature is really nice. You can see the ribs of the airplane and all that. I mean, it's and this thing is pretty fast as well. This is a sort of around 9 to 10 micron cutoff wavelength. Okay, so let me kind of summarize a little bit about sort of the state of the technology. So really from 3 to 5 micron, large format has definitely been demonstrated, and then I would say this is closest to commercialization. For the 8 to 12 micron, up to 11 micron cutoff has been demonstrated, and then for very long wavelength for hyperspectral, this definitely needs further development, and that's something we would like to pursue at some point as well. And then obviously there's multiband like shortwave, midwave, 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 mid-long, and long-long for the various applications. So there's a lot of room to grow. I think this is sort of a baseline technology, and I think if we have a good platform, then there's definitely opportunities to make use of this. Whoops, oh, sorry. Okay. So in terms of the cost to develop this, so pretty much I would say for each band, by the time you really put the efforts into doing it, it's probably about $500,000 to $1 million to kind of work with someone on this, because you have to iterate a few times, and that's just the nature of the beast. And then for the multiband, then that adds a complexity, so probably a little bit more money. But certainly, I think as we get better at this, hopefully we could definitely reduce the development costs as well. So why should NASA fund this? Well, or industry and other agencies, we feel this is the enabling technology that's going to serve as a platform for a lot of the future work that can come out of this. So, you know, there's various NASA missions that can benefit from this potentially, and in terms of high performance, lower cost alternative to mercatelluride, and then a large format with high yielding pixel possible. And then there are other applications in environmental sensing, industrial, and then biomedical applications as well. Okay. Oh, and this is my contact information, and I'll skip to the next slide. And in summary, so we have expertise in epi growth capabilities, and so the type 2 superlattice detector has high performance, manufacturability, and large format advantages. And then we also have flight experience to some degree, so we think that this is a legitimate way. And we have a very comprehensive manufacturing capability from substrate all the way to epi. And then and next, I'm just going to show a video that was actually the focal plane array that we delivered to JPL. So here they're doing the ice bucket challenge with the midwave, okay? Yeah, they asked me not to play the sound because it sounds a little embarrassing. Oh, wait, no, that's okay. So she was pregnant at the time, so they didn't let her do the ice bucket challenge.
Can you say anything about the noise equivalent temperature difference that you can detect in each of the wavelength bands, please?
Yeah, you could actually get very good noise equivalent temperature like in a long wave. It's like NEDT of like around 20 millikelvin or something like that. So this stuff is very good. I mean, there's certain. I mean, I could probably share with you some data sort of offline. Okay.
Hi, could you quantify how the type 2 SLS compares in detectivity with mercatelluride?
Oh yeah, the detectivity is actually, for a single pixel MCT, the quantum efficiency is generally better, but Mercat telluride, it's probably like, say you could do, typically say, a certain band, like, 80% with MCT, you could maybe get about 60% with type 2 stuff. But the difference is when you try to make a focal plane array, so if you make a single detector, get an MCT, that's fine. But if you want to make a focal plane array, you need good uniformity, because otherwise your image quality will suffer, right? If you have a background non-uniformity, and then with MCT you cool it down, you bring it back up, the characteristic changes. Like with type 2, you could basically do a factory cow and then ship it, and the baseline is stable. With MCT, you have to like do all kinds of expensive corrections.